Okay, so we're now going to look at the way to get the correct answer for question 1D, okay, in determining the pH of a solution if 0.1 moles of sodium hydroxide is added to half a litre or 500 centimeters cubed of a solution of known concentrations of the monoprotic acid, propanoic acid, and sodium propionate, also known in a certain concentration. We're also going to be given the Ka of propanoic acid, and it's 1.26 times 10 to the negative 5 moles per decimeter cubed. The first thing we have to get a handle on is what reactions are happening in terms of the buffer system. So what happens if we add hydroxide to the system, and what happens if we add protons to the system. Okay, because essentially in buffer reactions you can either add a small bit of base or a small bit of acid, and then there are slight changes as the equilibriums shift to make up that change. Okay, so there's two possible equations if we add hydroxide or we add acid. So the first one is if we're adding hydroxide, okay, CH3COOH, which is the acid, we add some hydroxide, and that's going to be in equilibrium with the associated conjugate base plus water. But because the hydroxide is a strong base, then it tends to favour the right. Okay, that's reaction number one. Okay, the second reaction that could be happening is that we have the conjugate base reacting with protons and going back to form the monoprotic acid, propanoic acid in this particular case. Okay, that's equation number two. Okay, so in the first question, 1D, we're going to be focusing on 1. We're actually adding hydroxide. Okay, so what the question says is that we must calculate the pH if the solution, if 0.1 moles of sodium hydroxide is added to 500 centimeters cubed of solution. Okay, so what we need to consider are the concentrations we have, the initial concentrations. So looking at our question, we can see that the initial concentrations of the conjugate base, the propanoate, is given as 0.05 moles per decimeter cubed. Okay, we are also told that the initial concentration of the propanoic acid, which we will do shorthand as HA, will equal 0.1 moles per decimeter cubed. We are also told in the question that the number of moles of hydroxide will be equal to 0.01, and the concentration therefore is going to be number of moles divided by the volume, which is going to be 0.01 divided by 0.5, because we are told there is 500 centimeters cubed of the total solution. Okay, so that will equal approximately, well, definitely 0.02 moles per decimeter cubed, the concentration of the hydroxide. Okay, so in terms of our first equation, we now have this guy, we now have this guy, we now have this guy, and we don't worry about water because that is the solvent. So how is the concentration of the acid and the conjugate base going to change as we add hydroxide? That's the next point. Okay, so we know from our notes that Ka is given as the concentration of A minus times the concentration of H plus divided by the concentration of HA. And we're told for this particular example that the Ka is 1.6 times 10 to the negative 5 moles per decimeter cubed. So we also can start to plug in numbers. Okay, so for this particular example, A minus is going to be based around equation 1 here. Okay, so A minus is going to increase because you're, of course, adding more hydroxide, and it's going to increase by 0.02 moles. Okay, so A minus is going to equal 0.05, the initial concentration, plus 0.02. Okay, which equals 0.07 moles per decimeter cubed. Okay, right, and we also can work out the concentration of HA because it's going to go in the opposite direction. Okay, as this guy starts increasing in concentration, this guy is going to be decreasing in concentration appropriately as it's being converted into the conjugate base. Okay, so it's going to be equal to 0.1 minus 0.02, which equals 0.08 moles per decimeter cubed. Okay, so far so good. So now we can determine that 1.26 times 10 to the negative 5, which is the Ka of propanoic acid, equals 0.07 times H plus, which is what we're trying to aim for to work out the pH, divided by 0.08. Make it a little bit more squarey brackety, but there you go. 0.08. So if we rearrange the equation, the proton concentration will equal 1.26 times 10 to the negative 5 times 0.08 divided by 0.07. Okay, and that now equals 1.44 times 10 to the negative 5 moles per decimeter cubed. So we're nearly there. Okay, and we know that pH equals the negative log base 10 of the proton concentration. So that will equal negative log base 10 of 1.44 times 10 to the negative 5, which will equal 4.84, which is the answer we are aiming for. Okay, so that's one approach to solve that problem. There is a second approach. You can use the Hollenbach-Henderson equation. Okay, and the Hollenbach-Henderson equation, of course, is pH equals pKa plus the log base 10 of the conjugate base divided by the acid. Okay, and we've already calculated these values here for A minus and HA, so we going to have to work out what pKa is. Okay, so the pKa is going to be the negative log base 10 of 1.626 times 10 to the negative 5, which equals 4.9. Okay, and so therefore the pH will equal 4.9 plus the log base 10 of A minus, which we have been given previously, which is 0.07 divided by 0.08, which will equal 4.9 plus minus 0.06, which equals 4.84, which again is the answer we are looking for. So there's two ways to approach this. You can either use the Ka calculations, which I recommend, it's more step by step, or if you can remember it, you can use the Hollenbach-Henderson equation, and which is a good approximation, and they both provide the same answer.